Hi, good morning, and welcome to the ZP Developer Zone. Every Thursday at 8 a.m. UK time, we like to do a webinar specifically for the members of our essentially our ZP Developer Zone. So what I'm going to do then is essentially jump into it now, and let me just do that. We like to do just checking that I basically had the volume. That was all. Okay, so if we jump into it now, every week we do the ZP Developer Zone. I do put this slide up. I say, if you're new to biosensors, you want to learn about biosensors, then we do have the ZP Academy. I do think a lot of the questions we get are answered through the ZP Academy, and there are 2 free courses on the ZP Academy that are essentially worth watching. And they are free. So if you go to the ZP Academy and look for free, you'll find a couple of courses. We do the webinar every Thursday at 8 a.m. UK time, and we also have our collaborations. It's probably worth saying that we have a member of the ZP Developer Zone coming to our facilities in the United Kingdom, so we're really happy, let's say, for that to also be happening as well. And also we do offer jobs up to members of the ZP Academy, or rather Developer Zone. We also have the Developer Zone website as well. Let's say I just wanted to check that the volume was coming through correctly, but it does seem to be coming through. Okay, and we also host workshops. We are hosting a workshop with Elsevier in Spain, but if there's interest, we will also kind of hold a ZP workshop as well, where we'll sort of teach on biosensing. Now every week we like to answer some questions. I think I want to go a bit quicker in my talking now. So let's say we've had some questions about electronics for ion-selective electrodes. So the inquirer is interested in doing water testing, probably continuous, fairly remote in the environment type water testing. So we will discuss that this morning. Another inquirer wanted to know about essentially glucose sensing. So we will cover that this morning. And also another inquirer was asking about essentially immunosensors, so we will cover that. And then another inquirer was asking about nanopores, and we will answer that very quickly. That one will be quite quick. And then also an inquirer that came in kind of fairly late last night about interdigitated electrodes, and we'll also just cover that quickly. I do want to go a bit quicker because that's 5 questions and it's quite a lot. Our lowest cost option for anyone looking for electronics for ion-selective electrodes is this sort of GFET board that we have that works with ion-selective electrodes. It's quite a simple and fairly open piece of hardware. I mean, most of the time, if people are looking to do biosensor development, I'll tell them to go and get a potentiostat. But if they're really looking for a low-cost, more open platform, then this is okay. This is one of the boards that we use to make, let's say, genuine products from. Now, the way it works is it's powered by a USB. So it gets its power and its telemetry by a USB. You can use a COM sort of terminal type program. It's essentially what it's doing is all the time the device is actually, once it's powered, is actually, I want to say, spitting out or sending a constant stream of data. I just want to say hi to Aftab this morning. Nice to see you, Aftab. So when it's powered, it's basically sending a constant stream of data. So in some ways, it's fairly dumb, the electronics on board of this. You power it up, it starts giving you numbers. The numbers could be, if there's no sensor in there, the numbers are sort of essentially gobbledygook. But if there's a sensor in there and the sensor's in a solution, then it's giving you a stream of numbers, which is actually a voltage, and that voltage is proportional to the analyte of interest. So this is the sort of lowest cost way of, if somebody comes to me and says, I want to do pH measurement or nitrate measurement, and they're trying to be low cost on us, then this is the board that I would recommend. Now the board comes in really two flavors. One of them is for what I say ion-selective electrodes, basically making potentiometric measurements, and the other one is amperometric. It basically measures current. So there are two flavors. The only difference between them is the firmware, but we have to do that in the factory rather than you can just change between voltage and current reading. Eventually I'm sure we'll get that so that you can, but at the moment it's not, unfortunately. We kind of provide it more as a service rather than an actual product. If people want it, we'll do it, but I think you need to be a bit of an engineer to engage with that. Just regarding, if you want to have a low cost sort of first go at measuring ions, then the board above in the previous slides was the good one to do. That will work with our pH sensor, which is ion-selective electrode, chloride, potassium, calcium, nitrate, ammonium, sodium, phosphate, and it will also work with something called ORP, oxidation reduction potential. Now, the reason I've done all that is the inquirer is interested in ions and they're interested in oxygen. So all the ions can be done with an OEM board, which is configured for the ion-selective electrode mode, and all those ion-selective electrodes will essentially work with it. So you've got one board that will do all the different sensors and therefore all the different ions. Oxygen's a bit different. It just occurred to me last night about the oxygen. So I've highlighted oxygen a bit different. I think this is kind of interesting to some of us that are a bit more geeky on this stuff, that you could measure oxygen using essentially a redox probe, a reduction oxidation probe. Now a redox probe, all it is actually a platinum electrode. And you can also measure oxygen in an amperometric mode. So at ZP, we tend to actually measure oxygen in the amperometric mode. But I kind of realized that if you're doing product development, and most of your electrodes are ion-selective electrodes, you don't really, and therefore you're measuring voltage, it's a bit of a pain to then have to measure current for just one of the sensors. But so you can theoretically measure oxygen concentration using what's called the ORP, which is really just measuring the voltage on a platinum electrode. And I did a very brief bit of, I knew it. I'd learnt it as an undergraduate. I remembered it last night. I did a quick search on it. And obviously, I did get a lot of results back on it that, it is a way of measuring oxygen. So you can measure oxygen essentially using a platinum electrode, using voltage as the signal, and, you'll get a voltage that's proportional to oxygen. The electrode that I would recommend for trying this, and I say trying because most of the time at Zimmer Peacock, we're able to recommend things that we do either routinely or we have at least done in the past. I haven't tried this one. I've a strong suspicion it will work, and I'll be annoyed if it doesn't, but that would be my recommendation, is to use the ion-selective board that I showed on the previous slide. Use one of these essentially platinum electrodes in there and measure the voltage as a current of as a function of oxygen. Now we do, and I will put any kind of link that I put in these slides, I'll also put it underneath the video as well. We often measure oxygen actually using an amperometric mode. So when you look at this data off our website, it's not voltage versus time, it's actually current versus time. So, but to do this, you need the amperometric version of that board rather than the potentiometric version of the board. As I say, it's the same board, it's just different firmware, but we haven't got it so that you can change the firmware yourselves. Now with the oxygen sensor, the way it's working is we're actually applying a negative voltage and we're reducing the oxygen essentially to water. And then when we deoxygenate, the signal kind of goes from a magnitude of 4 here to a magnitude that's much closer to 0. So that's a sort of deoxygenation event. So let me summarize this. If you're looking for a low cost way of measuring ions, then we call it the GFET board, but the GFET board is the best way of doing it. You can also use that to measure oxygen. Oxygen is slightly unusual that we could actually measure it using a amperometric mode or a potentiometric mode, I suggest you actually try the potentiometric mode, because then everything you're doing is very consistent. But at ZP we don't often use a potentiometric mode for oxygen. We actually use the amperometric mode, which means different board, and essentially not the platinum electrode, but actually an oxygen electrode that we also have on the website. It's not easy getting into biosensors. There's a lot of nuances, and that's why we do this webinar once a week, because we know it's not necessarily straightforward. Now we had another inquiry, and here the guy wants to know how to deposit our glucose activation solution on a wire. So on the wire, I presume he means a platinum wire. My first answer is I would use what's called a gas burner to give you a very blue flame. So the reason being is if you're going to use platinum wire, then the easiest way of making sure that it's in good condition is actually just to put it through a very hot flame, not a sooty flame. You don't want to cover it in carbon, but a very hot blue flame. So essentially, it'll just burn off any rubbish, and give you a pristine surface. Then you should actually be able to do essentially a good deposition. So I'm picking up specifically on the idea that you want to use a wire. And then he wants to know how to store the solution for long-term stability. So I will address that as well. First thing is you need two solutions. One of them is the activation solution, and you will also need a barrier layer as well. The barrier layer will give you the kind of linear range that you need. If you don't use a barrier layer, you might get a good signal between 0 and 5 millimoles of glucose, but then the signal will plateau, and it's because the enzyme is essentially saturated. So you need to have a barrier layer to limit the glucose. So first of all, you need two solutions. The solution that you should be most concerned about in terms of shelf life is the activation solution. Now what we do with the activation solution is we actually ship it in two parts. We ship the solution itself and we ship the enzyme. So you don't just, the reason I say it like that is because obviously enzyme in solution will denature. In order to prevent or to give you longer shelf life, we don't actually ship the enzyme in solution. You actually add the enzyme to solution at your site, and that will give you better stability. And we suggest you do it essentially in little aliquots, so you don't just take all the enzyme, put it in all of the solution, because then the clock is ticking, that the enzyme is going to start denaturing. We suggest you take out a little bit of the solution, put in a little bit of the enzyme, mix them together, and then use that to activate electrodes. I'm just going to back up a bit now and think, right, so if you're using a wire, and it sounds like you're using a platinum wire, you don't say it, but I'm inferring it, then I would put the wire through a flame to make sure you get pristine, basically pristine surface. Don't worry about the shelf life of the activation solution, because we actually ship the enzyme and the solution separately, and you will bring them together just before you use them, and that will give you a kind of good shelf life then. Unused material, let's say you had a little bit left, you could sort of store it at 4 degrees C. But once you put enzyme in solution, the clock is ticking, that it will expire. And, I can't really recommend storing enzyme solutions for long periods. They just don't like it. Now I'm going to go to question number 3 here. Now question number 3 here originally came in with the idea of actually making custom screen printed electrodes. I'm not a big fan of doing custom screen printed electrodes, because it essentially says I'm a company and I'm going to commission a screen printed electrode for myself, and I probably want to do it at quite low volumes. I don't want millions of screen printed electrodes. I might want thousands, I might want tens of thousands, but tens of thousands of screen printed electrodes is low volume. High volume is millions. So it's always a bit worrying when people want to do custom screen printed electrodes. It's not, because you're essentially putting all of the costs of doing that work into only a few thousand electrodes. If you're going to put the cost into developing new screen printed electrode, you want to spread it over millions of electrodes. So what often happens in the screen printing industry is that people will do this kind of work, but there's really no look on the quality. They just do it, it looks fine, but actually once you start electrochemically testing or using these devices, they're really not good. They're not repeatable. There's contamination. Next time you get a batch of electrodes, they're different. It's really quite broken. So now what these people want to do is make an immunosensor. So my first recommendation is our hyper-value carbon electrodes. We make a lot of immunosensors on top of this. My next recommendation, I'm going to speak quickly because Aftab's seen this before. Read this paper. It's free to download. In it, I'm one of the authors. In it, we tell you, look, take a carbon electrode. Carbon is good these days. Gold and platinum prices are really high. What you do is you first of all can sort of characterize the surface by cyclovoltammetry using ferrocyanide. You can immobilize a linking molecule. I think this is pyrene NHS onto the surface of the electrode. So now you have all these coupling molecules poking up from the surface. You can do a CV just to check the surface. Then you can bring your antibody in. This is really quick. It's kind of click chemistry. Well, it's easy enough to do, let's say. And then you can bring in your BSA, your blocking. And when you do that, you should find the cyclovoltammetry gets significantly changed, let's say, by the blocking material. Testing the electrode. I'm really sorry, Aftab, we've done this before. Testing the electrode. Test with ferrocyanide. You'll get a certain signal. We are using differential pulse voltammetry here, DPV. Add in some antigen, retest. Every time you add in antigen, the signal changes. I've said it before, and the guys who attend quite regularly know this. This paper's unusual because we're essentially blocking the surface and yet the signal is going up. That is unusual because if you block something, you'd expect the signal to go down. I haven't really thought it through. My guess is there's some sort of electrostatic interaction between, in this case, the HCG and the ferrocyanide. So I have not proven this, but it's unusual because I would expect, as you change the analyte, I would expect as the analyte concentration goes up, I would expect the signals to have actually decreased, but this is unusual. And when it's unusual, it might be because there's a favorable electrostatic interaction rather than just a blocking interaction. So it's worth reading the paper. It's worth getting hold of the hypervalue electrodes, and we use them a lot for immunosensors as well. Just a few comments. When you're doing the actual analysis of a new immunosensor, obviously try square wave voltammetry. It is sensitive. Differential pulse voltammetry is good. We actually prefer impedance spectroscopy. So we do have an impedance spectrometer ourselves. If you've got something like a palm sense impedance spectrometer, that will also work perfectly well. So just linking, what you will need is these connectors. Now with these connectors, I'm sorry to be sort of all technically detailed here. We have a connector that takes our 7mm screen printed electrode. So you need the connector that takes our 7mm width connector, and you need the connector that takes the 3mm banana plugs. I say that because most people who use in biosensing either use the ZP potentiostats or something like PalmSense. PalmSense has it's really bad, I know, a 3mm banana plug. We have a 3mm banana plug. People like Autolab have a 4mm banana plug. So for our screen printed electrodes and for the hypervalue electrode, you need the 7mm width slot, so you can slide in the screen printed electrode, and you need the 3mm essentially holes on the back here for your banana plugs. Sorry about all of that. And I recommend the hypervalue carbon electrodes. Functionalizing the electrodes. This is too much detail, I know, but we actually, when we do this kind of work, we do something like 60 sensors at a time. We test a few of them, make sure that the batch is good. We dispense on something like 3 microliters of the coupling agent. We leave it there for 4 hours at 4 degrees C. and that should be enough time for, you know, the sort of binding between the coupling agent and the carbon electrode. We test, and we then dispense the antibody on there. We leave that at 4 degrees for 4 hours, and that should be pretty good. So a few of them, just checking that we're streaming okay, and we test, and then we do the blocking material, and we do that. We put that on for 4 degrees for 4 hours as well, and then we essentially test, and then we actually start testing with antibodies itself. It's probably worth saying that you need something like 60 electrodes to sort of go through this kind of workflow. And I think it's probably worth saying that when we do this kind of work, I mean, this is not the world's best results, but, you know, to get these results, we had to put in something like 111 hours worth of effort. So, you know, I think Immunosensors can be quite a lot of work. So be expected for that. I mean, we often have a team of something like 5 people doing this kind of work at a time. I'm going to very quickly go over this. The screen printed electrodes that I recommend are pretty good because actually we do a lot of what's called wafer mapping. I think we're the only ones who do this. It just means that we test the batch using electrochemistry before we ship it, so we know we're not shipping stuff that doesn't electrochemically work. So that's a sort of difference. How you actually functionalize the electrodes is this. You sort of take the working electrode, which is the central part here. This one is a gold one. You don't flood it like that. Flooding will just put everything everywhere. We actually just put 3 1 microliter drops along here, and they often merge to give you 1 drop here. Now the particular person who's inquiring makes lateral flow strips, so they should have robots like we have for actually doing that kind of dispensing as well. So that's how you do the dispensing. I sort of wish you good luck with it in some ways. You've got to be very careful with the drying as well. We sometimes do this under vacuum. And also, if you're really doing biosensor development, you've got to do it at quite high numbers. You know, we're using multi-channel potentiostats to do our kind of testing. It's probably worth saying we're doing it in a clean room. And it's probably worth saying that you really need to take very good care of your data. I think, you know, when you're really doing a industrial powered immunosensor development, you need to know where your data is. You need to be able to share your data, and you need to be to analyze your data. So we have a system that we use internally called Julie. We make it available on the web. You can subscribe to it. So I would recommend you know where your data is, and Julie's a good way of putting electrochemical data in the cloud. Finally, I do feel like I've gone on a bit here, but finally, be careful about going for a bespoke screen printed electrode too early on. I have a whole article about this which says, you know, what's wrong with screen printed electrodes, and fundamentally what's wrong is companies too early on go for customization and then get very disappointed with the quality, the cost, and they actually get very disappointed with the repeatability, both within the batch and from batch to batch. And it's because basically they're trying to have a very bespoke product for themselves, and they can't share the cost over a large enough volume to make that economically viable. So my recommendation is, you know, jump onto the Hypervalue platform. We produce this in the absolute millions these days. Which means you essentially get the volume discounting, let's say, because we produce so many of them, and you also get the volume discount and the quality. So just FYI, that would be my recommendation. This is a bit of a warning, but it's something that I've had, you know, conversations I've been having with guys around the world. Is there's something very funny when we're buying equipment in Europe or selling equipment in Euro. There's a certain price. By the time it gets into some countries, the pricing is going from, you know, here to here. You know, it's really jumping up. You know, sort of 2x and 3x. So just be careful when buying potentiostats and screen printed electrodes. Just know that, for example, with a Julie license for a year, we're giving away 500 screen printed electrodes, a USB potentiostat, and the 12 months. Now we do all that for €949, but I flag it up because I know in some countries people can't even get, you know, the potentiostat for that kind of pricing, and we're bundling it up with screen printed electrodes, and we're bundling it up with a Judy package as well. So just be really careful. There's something going on when these sort of products are leaving and going to different territories around the world. The pricing is really changing. I mean, similarly, I think one of the more popular low-cost potentiostats out there is the PalmSense Sense-It Smart. You know, we're bundling the PalmSense Sense-It Smart plus 200 screen printed electrodes and 12 months of Julie for €948, and I know that people are spending much more than that just on the potentiostat itself. So just as a warning, this is slightly something different now. I'm going to go a bit quicker because we are running out of time. We did have some inquiries recently about nanopores. It's not something we very rarely talk about, nanopores, but it is actually quite interesting. I think the key name in this kind of field is a company called Oxford Nanopore. I heard the other day that they had a valuation of 24 billion, so well done to them. The CEO is a guy called Gordon Sanghera. I used to work with a guy 20 years ago, but the reason I'm jumping now into nanopores a little bit is we just had an inquiry about it. It was very interesting actually to get that inquiry. I mean, what happens with a nanopore is this, that I'll go a little bit quicker. What you do have is you have a disk of silicon in the approximate center of which you have a hole of about 20 nanometers. So you put this disk between two solutions, and what happens is you then put an electrode either side of the disk. So you put a silver chloride electrode either side of the disk, and you essentially apply voltage. So you've got an electrode, a disk, a hole in the disk, and then the other side of the disk another electrode, and you apply voltage. And what happens is you get a very small current because basically 20 nanometers is like a massive resistor. But as interesting molecules like DNA go through there, they end up blocking the hole for a brief second, and the impedance jumps up. And if you're very clever, then actually, depending on the bases, if it's an adenosine, or so is it A or a G base, you actually get different profiles. So it's not something we talk about. We did get an inquiry this week. I think ZP is kind of interested in getting into nanopores more than we have been historically. It's quite simple in theory. The experiments, I suspect, are tricky as anything. Yeah, Aftab's just saying that nanopores are interesting. And what's interesting, Aftab, as you made the comment, is we've just got ourselves a new e-beam facility, so the ability to make nanopores, you know, we just went up a big time in doing that. That's why I'm kind of getting interested in it. So we do have some kits for nanopores, and we do have the knowledge. We also have the electronics. It's so we are something we're going to get into a lot more. I've been interested in it, I don't know, 10 years now, but it's been around. It's a technology I think that originally came out of Oxford. I want to say about 15 years ago, but it might be longer. So really more than comments. Last thing, interdigitated electrodes. So we get inquiries about interdigitated electrodes. I've got a couple of problems with interdigitated electrodes, maybe 3 problems. Interdigitated electrodes are actually quite expensive to make. They tend to have low yield, and they actually don't do any better job, I think, than actually more macro electrodes. So let me explain that. So an interdigitated electrode, Aftab knows this, you know, you've got 2 electrodes which essentially have finger-like protrusions from them, and these finger-like protrusions weave together, and you can measure, you know, impedance between these electrodes, and you can build biosensors upon them. Now, what we did first of all at Zimmer and Peacock is we thought, well, really these are just essentially wires in close proximity with one another, and so we'll make a spiral electrodes and, you know, use that instead of, because we think we can make a spiral electrode at lower cost, higher volume, higher yield, and it's better. So I used to go around saying, okay, if you wanted an interdigitated electrode, let's use the spiral electrodes instead, because I think I can give you a better price. What we discovered over the years, and this was really quite shocking to me, is we were doing some conductivity measurements. So conductivity, you know, is a application of impedance measurement. So we were doing some conductivity measurements, and we got a probe from Mettler Toledo, a conductivity probe, and we measured the sort of sensitivity and the offset. So we took different solutions with different conductivities, and we tested the probe with it, and we made essentially a calibration curve. And then we did it with our spiral, and we said, oh, that's really good, because, you know, if you want to have a kind of, you know, what's a gold standard for making a impedance measurement? Well, we'll use a lab conductivity sensor to kind of have that gold standard and see how we compare. And we compared, you know, really, really favorably. And then a few years later, we ended up testing some of our other screen printed electrodes, which didn't have any fancy spiral or interdigitation, and we got exactly the same results. So there's this idea, and I get the maths and the physics of this, that interdigitated electrodes, you know, the thinner they are, the smaller the gap, the better the signal. But I actually think that in reality, when you actually make electrodes on tops of normal screen printed electrodes, you get just as good signal whether you went interdigitated, spiral, platinum, plates facing one another. They all gave us the same signal. So I do understand why people ask us for interdigitated electrodes, and there is a lot of literature about it. And our own journey is, you know, we've gone from interdigitated to spiral, and then we actually discovered that just standard screen printed electrode geometries gave us just as good results. And so, and the thing about that is, you know, we can produce, you know, like these hyper value electrodes, you know, small packs of 200 at like 99 cents each. You know, it's kind of crazy, really. So it just, you know, especially if you're going to make a product from this, you know, you do need to be working with geometries and materials that you actually can scale. And so I would say that sometimes interdigitated is a little bit overhyped. And Aftab saying here that, you know, see, interdigitated electrodes are made by sort of masks and sputtering in clean rooms. And, you know, at high volume, it could be low cost, but the reality is it's always lower cost to just print the stuff in the first place. All right. And any links that I put in these slides, I'll also put in the video below. I realize we're 3 minutes over. So thank you for the question on electronics for ion-selective electrodes. The GFET board is good. You have to use a terminal program to get the data off there. You can probably use it for everything. I'd even try it with the oxygen, even for measuring oxygen. The glucose activation solution, don't worry about the shelf life. The enzyme comes separate. Just put it in at the end. But do it in aliquot. You don't want to waste that material. Immunosensors and custom screen printed electrodes, just use the hypervalue carbon electrodes. We use them in the thousands and the tens of thousands for making immunosensors. I think there's enough material in this presentation to kind of get you going on that. Nanopores, just more interest than anything, something that we're interested in at ZP. And then interdigitated electrodes, our own journey has been, you know, from interdigitated electrodes to spiral, from spiral to actually standard screen printed electrodes, and the results were really the same. So I just want to say, you know, thank you very much. I appreciate that was something like 34 minutes. It was a little long, but there were a lot of questions. Next week, I think I'll be doing quite a lot on glucose sensing. I seem to be getting a lot of questions in at the moment on glucose sensing. So sorry that we returned to the topic, but thank you very much, Aftab and guys, for your attention today. And this video will be left up online, so if you want to follow it later.